property associated with the system's stability. Now, what stability implies? Well, first of all, informally, you can say a system is stable if a system is stable in is the one in which the small input leads to the response that does not diverge. So, for a small excitation or a small disturbance, you don't have an output from the system that is divergent. Okay, you don't have an unbounded or a response that is growing without bounds out of the system. So let's consider an example of a stable pendulum in figure 146a. You see over here, if the input of the system is a small force xt applied, the pendulum is supposed to shift from its initial position, and the output over here is the angle with a vertical yt. So for a small excitation or a small applied force xt, you have a small, or let's call it a bounded deviation from the initial position. Okay, so yt is non-zero. You will get a non-zero angle. So, but then again, for such a physical system, considering the gravitational forces, the gravitational forces will be as such to bring this pendulum back to its initial position, and due to the drag, there will be the frictional forces that is going to retard this motion back to its initial position. Okay, so for a small excitation or disturbance, you have a small output angle y of t, and this is a stable system. Okay, but if you consider an inverted pendulum in figure B over here, what happens is that even for a small excitation xt, your output, the angle with the vertical, it grows. It grows without bounds. Okay, I mean, even in the presence of frictional forces, retarding forces, the act of the gravity will be as such to make the output y of t divergent. Okay, I mean, this pendulum is going to fall. So the output y of t is divergent. It's not bounded. So what happens is, again in figure 146a, in which the input is applied force xt, and the output is the angular deviation yt from the vertical. So in the first case, the gravity applies the restoring force that tends to return the pendulum to the vertical position, and the frictional forces due to the drag, they tend to slow this motion down. So consequently, a small force xt is applied, and the resulting deflection from the vertical will also be small. But in contrast, for an inverted pendulum in figure B, the effect of gravity is to apply a force that tends to increase the deviation from the vertical. Okay, so the effect of the gravity is the opposite in figure 146b, as you can see over here. So this y of t is going to be, it will be unbounded. Okay, it's an unstable system. So 146b is an unstable system, 146a is the stable system, so that for a small excitation, your output is not growing, your output is not divergent. Okay, but in the later case, in part B, the yt is divergent. So you see in the inverted pendulum case, a small applied force, it will lead to a large vertical deflection, causing the pendulum to topple over despite any retarding forces due to friction. So if the system response grows without bound in response to small inputs, it is unstable. It is an unstable system. Okay, so that's the definition of a stable unstable system. So you see over here, 146 is an example of a stable system, while an inverted pendulum is an unstable system. You see, even for a small excitation, you have a large diverging output. The vertical angle is growing, and it gets toppled over. So that's the act of gravity. So yt is growing. So this is an unstable system. Okay. Similarly, we have another electrical system. So, for example, if you consider a simple RC circuit, you see the capacitor stores the energy in electric field between its plate due to the charges. So if this energy gets dissipated by the dissipative element, that is the resistor, so the resistor dissipates energy. So the system is stable. The output is not growing, okay, because the resistor is consuming that energy stored in the electric field of the capacitor. So physically, stability of a physical system generally results from the presence of mechanisms that dissipate energy. Okay, so formally, if you have to put this example in a formal manner, though these preceding examples, they provide us with an intuitive understanding that the concept of stability, and formally you can put it like this: that if the input to a stable system is bounded, so if the input is bounded, it means its magnitude does not grows without bound. then the output must also be bounded and therefore cannot diverge. So therefore we cannot have an output that is diverging or unbounded. So an important thing to notice over here, it's about the magnitude. Okay, the magnitude of the input has to be bounded. So if you apply a bounded input whose magnitude is bounded, the output should also be bounded by some other bound. Okay, it could be some other arbitrary bound, but that criterion is more commonly, this criterion is more commonly referred in signal system text as BO stability. That is, the bounded input leads to bounded output, and this implies stability. Okay, so that's the criterion for stability. So as an example, for example, if what could be a stable input? How about if you have a discrete time system and you apply an input that is unit step function? U of n is a bounded input. Okay, U of n is a bounded output. What is the bound over here? If x of n is U of n, what is the bound? The bound is 1 because the magnitude of U of n is bounded by, what is the maximum bound? That's 1. So you see over here, for all n, the magnitude, this is always less than or equal to 1. So that's the bound. Okay. Now, if this system is applied to a certain discrete time system, dt, and the output, whatever is the output, let's call that y of n, and if that y of n magnitude is also bounded for all n, you see, for all n, we although this input u of n is an infinite duration input, right? I mean, u of n is non-zero for n greater than or equal to 0. U of n exists for n greater than or equal to 0. It's non-zero, so it continues forever, right? So we are not summing this up. The samples are infinite, we know that, but the magnitude is bounded, so it's a bounded input, right? But if you apply this to a discrete time system which applies certain transformation producing an output y of n, if the maximum magnitude of the output for all n is bounded, let's call this a bound. It is always less than a certain bound called that by. Then yes, the system is stable. The discrete time system in this question is stable, right? So the bounded input leads to the bounded output is a criterion for stability of systems. So suppose that what it says is that, again, it can be put it like this: suppose that the input x of n is bounded in magnitude, that is important, in magnitude, by some number b, then for all values of n, then if the largest possible magnitude of y of n is also bounded by some other finite number, let's say capital M, then y of n is bounded and the system is stable. Okay, so you have to see if the magnitude of the input is, first of all, you have to apply a bounded input, and if the output does not diverges, the magnitude of the output is also bounded for all the times by a certain bound, then you can say the system is stable. Okay, the output is not diverging. All right. So let's take an example of the accumulator. You see here we have an example of a discrete time system we have talked of earlier. So on the other hand, let's consider an accumulator. Now you recall that this system sums all the past values of the input rather than just a finite set of values, and the system is unstable. Why it's unstable? You see, what it's going to do is it's going to sum up all the samples from minus infinity to all the way up to the present time instant n. Okay, so dot plus, it's going to sum up till n minus 1. Of course, the system will require some memory. It's not a memoryless system, so it has to have some information of all the past samples. All right. So for a digital system, it might store this in registers, whatever. But it's a system with memory. Okay. So you see, if to characterize this system as an unstable system, what we do is we apply a bounded input. So for example, if the input to the accumulator is a unit step input, okay, the output will be, you can write this. I mean, this x is replaced by u of k over here, and the output is again n plus 1 u of n. So this, you see, the thing is, if you have to compute, you don't need to worry about the negative indices. It can start with 0, okay, because the first sample. So the thing is, y of 0 for the first sample of the unit step function, the sum is 1, okay, at n equal to 0. This is at n equal to 0. Then what happens is, y of 1, it's going to sum up the n equal to 0 and n equal to 1, and this is equal to 2. Similarly, y3 will be, again, just add 1 to it, so it will be 3, because the unit step function is like this, and you're summing up all the samples. So for example, if the output of the system at n equal to 0 is just 1, right? This is n equal to 0. So this is 1, this is 1, this is 1, and this continues. The trend is continuing forever, okay? Forever, for all the positive discrete time indices. So n is greater than 0 over here, greater than or equal to 0. And this is 1, this is 2, okay? So for example, over here, y of 0 is 1, y of 1 is 2. So y of 1 means, you can write this as n plus 1, right? N plus 1, u of n means that this output is also of infinite duration. Similarly, y2 is 3, right? So, and so on. So y of n is growing without bound. Why? For large n, this is not bounded. I mean, up until 100, 1000, there's no bound, right? We cannot define a certain bound. Although u of n, the magnitude of u of n is bounded. U of n, again, the magnitude of u of n is bounded by unity. The maximum magnitude that u of n can have is 1, okay? But over here, y of n is not bounded by any finite number. The magnitude of y of n is infinite, so is infinity, because it's growing with increasing n always, okay? So this is an unstable system. I mean, intuitively you can also think of this as, this is an accumulator, and it's going to sum up all the samples, infinite number of samples. So the output, the sum, is going to grow indefinitely, okay? So it's unbounded, so it's unstable, okay?